Hi, this is Aaryan Kapur of EB01 roll number 004, and today I'm going to discuss with you the dining philosopher's problem, which is a classic example of a deadlock problem. And now we will look at the problem, the explanation of deadlock, and what exactly are the solutions that are possible. So let's start.
Okay, so coming to the problem now. So let's imagine a scenario where five philosophers are sitting around a table. Now, a philosopher can do two things. First is think. Second, whenever they get hungry, they eat. So now let's imagine there are five chopsticks here, 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 here. That is one in between every two philosophers. Now, whenever a philosopher wants to eat, whenever a philosopher wants to eat, he can pick up the two chopsticks adjacent to him and start eating. Now, this a single white line denotes a chopstick, whereas a white line with a green circle denotes the chopstick is taken, and the arrow denotes to whom. Now, if you look into the diagram, for example, all of the philosophers are thinking, and suddenly philosopher 1 feels hungry. So now what does he do? He simply picks up a chopstick on his right, then picks up the chopstick on his left and starts eating. Now, simultaneously, let's see if philosopher 4 gets hungry. Now, philosopher 4 in a similar manner takes the right chopstick and now takes the left chopstick. Now, for example, philosopher 2 gets hungry before philosopher 1 is done. Now, philosopher 2 has already taken up the philosopher 2 has already taken up the left chopstick in his hand. But now he is still waiting for philosopher 1 to complete his meal. Now philosopher 2 is waiting. Now, for example, philosopher 5 wants to take the chopstick. He has no chopstick on either side, and so does, similarly for philosopher 3. Now, all of this is an issue because people have to wait. Now, I'll explain to you in what scenario a deadlock could take place. So basically, a deadlock is when one resource is waiting for another resource to one process is waiting for the other process to free up a resource, whereas it is holding the resource that is required for the second process to function. So now, for example, philosopher 1 picks up all the philosophers get hungry simultaneously. Philosopher 1 picks up the right chopstick. Philosopher 5 also does that. So does philosopher 4. So does philosopher 3, and so does philosopher 2. So now, as all the philosophers have taken up the right stick, now they go for the left stick. So now, philosopher 1 reaches out for the left stick, but he cannot find any. So now he knows that philosopher 2 is using it, so he'll be waiting for philosopher 2. Right, so he's waiting for philosopher 2. Now, philosopher 2, now when he starts eating, he also looks for the left stick, which is taken by philosopher 3. So, philosopher 2 is waiting for philosopher 3. Similarly, philosopher 3 waits for philosopher 4. Philosopher 4 waits for philosopher 5. And philosopher 5 again waits for philosopher 1. Now, as you might be able to see, this is a deadlock situation because philosopher 1 will never complete his eating until philosopher 2 is free, and then 2 cannot complete until 3 is free, then 3 cannot complete until 4 is free, and so on. So, in the end, this creates a cycle which cannot ever be achieved. So, this is a deadlock situation. Now, we will look at some solutions to the problem. Thank you. Hi. So now we will start discussing the solution to the dining philosopher's problem. So we will be looking into four different solutions and one improvement to one of them. So now looking at the first solution. So basically the first solution just suggests that we apply a priority based system, but that is not a very efficient method because if we give priority to say any two of them, the rest three will starve, and so on. So this is not a very ideal solution. Now looking at the second method, what we try to do is
In the second method, what we try to do is we try to ensure that this kind of a situation does not occur. So what we would try to do is whenever a philosopher is hungry. So whenever this is basically the checking method. So whenever the philosopher is hungry, they will pick up the right fork, pick up the right fork, and then look for the left fork. And if they can't find it, then they start eating. Else they starve. Basically, they keep back the fork or the chopstick. Keep the fork. Hi. So I believe there had been some issue where the recording had stopped in between, so I'm very apologetic for that. So now I will just rush through what we covered and then keep on going. So first one was the priority-based method. Now coming to the second method, every philosopher just checks if they pick up the right fork, then they check the right chopstick, and then they check if there's a fork or the chopstick on the left. And if it's not, they just keep it back and then start waiting for the predefined T time period. Otherwise, they start eating. So now this is though this does solve the problem to a certain extent, but this does not guarantee the solution, and there's a very high chance. For example, if every philosopher starts eating together, as explained in this example, then everyone will pick up the right stick, wait for the left one, will not find them, keep it back, and then wait for T seconds, and then do this all over again till infinite time, and they will all starve to death. Now we will try to improve the solution. So now once we go into the improved side of this, this is exactly the same, but except putting the T here, we just put the random time in instead. So there's a random time interval. So there's a better chance of not having this issue, though this does not guarantee a good solution. So now coming to mutex. So what we do is we use the mutex to protect the critical section. So now what happens is we use the philosopher function, and once while all the conditions are true, we go and the philosopher starts thinking. Then whenever they feel hungry, they log the mutex. They start and then they pick up the fork, right? The right fork, and then they pick up the left fork. They start eating, then they put back the left and put back the right, and then they unlock the mutex. So now this works because nobody can work that because no other philosopher can eat till the time the mutex is unlocked. But this is a very inefficient solution as only one person can eat at a time, and this is probably not a very good solution. So now we look to solve that using semaphores. So what happens is semaphores divides these activities into three. That is thinking, becoming hungry, and then eating. So now what happens is once the philosopher starts. So while the conditions are met, they start thinking. Then they pick up the forks, they eat, and then they put the forks. Now pick up the forks and take the forks are separate functions that I'll be defining in the M and the N category. So we first go to the M, that is the take forks. So once we start the take fork function, they log the mutex, they change the state to hungry. Then they the test function, that is O, that I will come to in a second. Now after that is done, they unlock the mutex and then they down the semaphore for that particular value. I will explain that too. Now we come to N, that is put forks. So now what they do is they again load the mutex, they put the state to thinking because the philosopher is done eating as they're putting on the forks. Now they test the left side, then they test the right fork, and then then they unlock the mutex. Now coming to the most important one, that is test. So what happens in test? First of all, what they do is they check three conditions. So one is that is the philosopher hungry? Then they check these all are required conditions and added to each other. So now they check for the left one. So is the left person eating? No. Then the left person should not be eating. That is the condition. Same for the right person should not be eating. If that is all true, then the ith person, that is the philosopher, can start eating, and then they up the semaphore. So basically, up means that they will increment the semaphore, and down means that if it's a zero, a non-integer, then they let it be. But if it's a non-zero number, that is 1, 2, 3, 4, they decrement the semaphore. Now, for example, there are 5 processes. So these all take chances in doing this. So if one of them wants to eat, they check on the left and right before picking up the forks, and they also check on the left and right while putting down the forks. And this is how it will keep on going. So thank you so much. Back to myself. Hi, this is Aaryan Kapur, and I'm from EB01, roll number 004, and I just explained you the Dynamic Philosopher's problem. Thank you so much for listening to me, and I hope you had a great time. Thank you.